wonder why matrix arithmetic matters in your day-to-day life? You might not realize it, but matrices are everywhere, quietly performing their magic behind the scenes. It's like the Wizard of Oz, pulling the levers behind the curtain. For instance, every time you play a video game or watch a CGI-enhanced movie, matrix arithmetic is hard at work. It's what allows for those stunningly realistic graphics and seamless movements. The images you see on the screen are made up of thousands of tiny pixels, each one manipulated and positioned using a matrix. The order of the matrix, which is the number of rows and columns it contains, determines the level of detail in the image. But matrix arithmetic isn't just for the world of entertainment. It's also a vital tool in physics. When scientists need to analyze complex systems, like the behavior of particles in a nuclear reactor or the movement of celestial bodies in the universe, they often turn to matrices to simplify the process. Each matrix they use is like a mini-map, representing a snapshot of the system at a particular point in time. And let's not forget about economics. When economists want to understand how different sectors of the economy interact with each other, they use what's known as an input-output matrix. This matrix allows them to see the flow of goods and services between sectors, helping them to predict future trends and make informed decisions. But before we can harness the power of matrices, we first need to understand what they are. A matrix is basically a rectangular array of numbers, arranged in rows and columns. The order of a matrix is defined as the number of rows m and columns n, and is denoted as mxn. Matrix arithmetic is like a secret language, a code that helps us to navigate the complex world around us. And just like any language, it has its own syntax and grammar, its own rules and conventions. Now that we know why it's important, let's dive into the different types of matrices. A matrix can take on many forms, each with its unique properties and applications. Let's start with a row matrix. This one's pretty simple. It's a matrix with only one row. Then we have the column matrix, which, as you might guess, has a single column. Next up is the square matrix, which has the same number of rows as columns. Think of it like a perfect square. And within this category, we have a couple of special types. First, the diagonal matrix. This is a square matrix where all the elements outside the main diagonal are zero, for instance. Then we have the symmetric matrix. This is a square matrix that is equal to its own transpose. In other words, if you flip it along its main diagonal, it stays the same. A triangular matrix is another type of square matrix. It's either upper triangular, with all the elements below the main diagonal as zero, or lower triangular, with all the elements above the main diagonal as zero. The zero matrix is pretty straightforward. It's a matrix where all elements are zero. This can be of any size, not just square. The binary matrix is a matrix with elements that are either 0 or 1. It's quite useful in computer science, especially in the realm of digital logic. Finally, we have the identity matrix, a special square matrix that acts like the number 1 in matrix multiplication. It's a square matrix with ones on the main diagonal and zeros everywhere else. It's quite the superstar of matrices. These different types of matrices give us the versatility we need in various fields of study and work. So, whether you're working in physics, engineering, computer science, or even art, there's a matrix out there for you, and now you're one step closer to understanding them all. The transpose of a matrix is a simple yet powerful concept. Imagine a matrix as a grid of numbers with rows and columns. The transpose of this matrix is essentially a mirror image, where the rows become columns and the columns become rows. It's like flipping the matrix over its diagonal. Here's how to calculate it. Take each row of your matrix and flip it vertically to become a column in the new matrix. The first row becomes the first column, the second row becomes the second column, and so on. For example, if we have a 2x3 matrix containing the elements 1, 2, 3 in the first row, and 4, 5, 6 in the second, its transpose will be a 3x2 matrix, with the elements 1, 4 in the first column, 2, 5 in the second, and 3, 6 in the third. With the transpose in our toolkit, we are ready to move on to elementary matrix operations. Matrix operations are the bread and butter of matrix arithmetic. Let's dive into the world of elementary matrix operations. We'll start with the sum and difference of matrices. To add or subtract matrices, they must have the same dimensions. That means the same number of rows and columns. You simply add or subtract corresponding elements from each matrix. For example, if you have a matrix with elements 1, 2, and 3 in the first row, and a second matrix with 4, 5, and 6 in the first row, the sum of these matrices would have 5, 7, and 9 in the first row. Next, we have the multiplication of a matrix by a scalar. A scalar is just a fancy term for a regular number. To multiply a matrix by a scalar, you multiply each element in the matrix by that scalar. For instance, if you have a matrix with elements 1, 2, and 3, and you multiply it by the scalar 2, your new matrix will have elements 2, 4, and 6. Then, there's the product of matrices. This operation is a bit more complex. To multiply matrices, the number of columns in the first matrix must equal the number of rows in the second. You then multiply each row of the first matrix by each column of the second, summing the products. For example, if you have a 2x2 matrix with elements 1, 2 in the first row and 3, 4 in the second, and you multiply it by another 2x2 matrix with elements 5, 6 in the first row and 7, 8 in the second, the first element of the product matrix would be the sum of 1 times 5 plus 2 times 7. These operations may require some practice to get a handle on, but they're crucial tools in the world of matrix arithmetic. They allow us to manipulate matrices in ways that can reveal important information about the systems they represent. These basic operations form the foundation for more complex matrix manipulations. Ever wondered what it means to raise a matrix to a power? Well, let's dive right in. The power of a matrix is similar to the concept of exponents with numbers. But here, instead of numbers, we have matrices. When we say a matrix is raised to the power of 2, it simply means that the matrix is multiplied by itself. Just like in numbers, where 3 squared equals 9, a matrix squared would be the matrix times itself. Now, let's take a quick example. Suppose we have a 2 by 2 matrix, say A. If we want to calculate A squared, we just multiply matrix A by itself. Remember, when multiplying matrices, the order matters, so be careful. So if you want to find A cubed, you would multiply A by A, and then multiply the result by A again. It's a bit of a brain teaser, isn't it? Knowing how to calculate the power of a matrix can open up new doors in your understanding of matrix arithmetic. Now that we've covered the basics of matrix arithmetic, let's summarize what we've learned. We kicked things off by understanding the order of a matrix, which essentially is the number of rows and columns in a matrix. We learned that the order is represented as m by n, where m is the number of rows and n is the number of columns. Then we moved on to different types of matrices. We explored many, including row, column, square, diagonal, symmetric, triangular, zero, binary, and identity matrices. Each has its own unique properties and applications, and understanding these can be incredibly useful in various mathematical and scientific contexts. We also delved into the transpose of a matrix, which is simply a new matrix obtained by interchanging the rows and columns of the original matrix. It's a useful concept that comes up in many areas of mathematics and computer science. Then, we got our hands dirty with some elementary matrix operations. We learned how to add and subtract matrices, which involves simply adding or subtracting corresponding elements. We also mastered multiplication by a scalar, where each element of the matrix is multiplied by a given number. We didn't stop there, though. We also explored the product of matrices, a slightly more complex operation that involves multiplying rows by columns to generate a new matrix. Finally, we looked at the power of a matrix, a concept that involves multiplying a matrix by itself a certain number of times. This is used in many advanced areas of mathematics, including solving systems of linear equations and